Hello again. So we've seen that the energy levels in a hydrogen atom uh, we've got the 1s orbital in the first energy level. The second energy level contains the 2s and 2p sublevels, containing a total of 4 orbitals. And then the third energy level contains the 3s, 3p, and 3d sublevels. And we've seen that in a hydrogen atom, or in a hydrogen-like atom where there's only one electron, each of the sublevels for a given energy level is degenerate. That is to say, all the sublevels in level 2 have the same energy, all the sublevels of level 3 have the same energy, and so on. And we've also seen that when you've got a hydrogen atom in its ground state, that is to say, when it's just resting in its lowest energy, that its electron will have a wave pattern that's described by 1s. And so we say that a hydrogen atom has its electron in the 1s orbital. Now, for more complicated atoms, such as helium, so helium has an atomic number of 2, and its first electron will go into the 1s orbital, just like the electron in hydrogen, but the second electron has a choice of where it goes. So one thing that we need to understand is that in an atom, every electron is different. So every electron has a different wave function. And so as far as we're concerned, what that means is that you can have two electrons that have the same orbital wave pattern as long as their spins are opposite. So you could have an electron with a spin going up and an electron with a spin going down in the same orbital, but you couldn't have two up spins in the same orbital, for example. And so the second electron has a choice. It can either pair up with the first electron in the 1s energy level, 1s orbital, or it could go up into the second energy level, either the 2s or one of the 2p orbitals. And the second electron doesn't like pairing up with the first one. When electrons pair up in an orbital, they are in the same region of space, and so they repel each other. But on the other hand, the 1s orbital is so much lower in energy than either the 2s or the 2p that the second electron is better off going into that 1s orbital and pairing up. And so the helium atom has its two electrons in the 1s orbital. Now, like I said, there is a penalty associated with pairing up electrons. Those electrons do repel each other, and that raises their energy. And so the 1s orbital in a helium atom is higher in energy than it would have been if there were only one electron. So the repulsions between those two electrons do raise their energy. They also raise the energy of the other energy levels as well. There aren't any electrons in those levels, but if there were, their energies would also be affected. And so you can see that as soon as we start adding more than one electron into an atom, all of the energy levels are affected, and the reason they're affected is by the repulsive forces between the electrons. And so pictures like this it gets very difficult to see exactly what's going on with the energies. And so I'm going to shift to a more schematic representation of the energy levels. And this is how the energy levels might be represented for a hydrogen-like atom where there's only one electron and all the orbitals in a particular level would have the same energy. And as soon as you start adding more than one electron, the different sublevels are affected to different degrees. And so this is what happens. The P sublevels get raised a little bit, the D sublevels get raised even more, the F sublevels get raised the most. And so the result is that if you look at the sublevels of an atom in order of increasing energy, it follows this kind of zigzag pattern. And one way that you can remember this, a mnemonic device is if you write out the sublevels of the different energy levels in the atom, and we don't really need to go past the F sublevel. There are sublevels beyond F, but they don't. They're not. They're not very common, and we don't need to worry about them. But the point is, when you've written out the energy levels like this, if you then draw in diagonal lines, they will show you the sequence in which those sublevels appear as you go up in energy. And so you can use this sequence to figure out where electrons are going to be in an atom. And so if we clear things out a little bit and get the top part of the periodic table, let's look at a few examples of atoms and how we can use this building up principle to work out what their electrons are going to look like. So we've already seen that in a hydrogen atom, the electron will go into the lowest orbital, which is 1s. And so if we wanted to, we could describe the electron in hydrogen as being, it's in the 1s orbital, and one way that we could write that is with this notation that's read 1s1. It's written as though it's 1 times s to the first power. We read it as 1s1, and this notation is referred to as the electron configuration of the hydrogen atom. Another way that we could represent the same information is by putting a little box to represent the 1s orbital and to have an electron sitting in that orbital with its spin either up or down. Traditionally, the first electron to go into an orbital is drawn with its spin pointing up. And this kind of picture that conveys the same information about what the electrons are doing in an atom is referred to as an orbital diagram. And so we can write electron configurations and we can draw orbital diagrams for any atom. Looking at helium, we've already seen that in a helium atom, the second electron also goes into the 1s orbital, and so it has an electron configuration of 1s2. The orbital diagram will reflect that. You'll have 2 electrons with opposing spins in the 1s orbital. And so since the first energy level only has that 1s orbital, once helium has filled in that orbital, the first energy level is filled up. And so you could say that helium closes off the first energy level of the atom. And so if you move on to the next element in the periodic table, which is lithium, lithium has an atomic number of 3. It has a third electron. There's no room for a third electron in the first energy level, so it has to go into the second energy level, and the first available orbital is the 2s. And so lithium will have its first 2 electrons will be in 1s, and then its third electron will be in the 2s orbital. Its configuration is 1s2, 2s1, and we can write its orbital diagram like this, with a pair of electrons in the 1s orbital and then a single unpaired electron in the 2s orbital. Now, before I continue, I want to say something about what happens when you start getting electrons in multiple energy levels in an atom. So if we look at the hydrogen-like orbitals in a lithium atom, in a hydrogen-like atom, if there were only 1 electron, you'd have the first energy level, the 1s, would be fairly small, and then the second energy level would be 4 times as big. The third energy level would be 9 times as big as the first one. The fourth energy level would be 16 times as big, and so forth. And that's all that is true as long as there's only 1 electron in the atom. But when you start having several electrons, then, well, for one thing, the electrons are repelling each other, and then for another, the nucleus is becoming more and more positive. And so in the case of a lithium atom, the nucleus has a charge of 3+, and so if you have 2 electrons in that first energy level, those 2 electrons are going to be strongly attracted by the nucleus. They're closest to the nucleus, and they're going to be experiencing that full 3+ attraction. And that attraction pulls those electrons in. And so the 1s orbital in a lithium atom is actually much, much smaller than it would be in a hydrogen atom. Now, the second energy level is also going to be pulled in by the stronger charge of the nucleus. But if you think about it, you've got, if there are 2 electrons in the 1s orbital, those 2 electrons are almost on top of the nucleus, and they're going to be repelling the outer electrons in the atom. And so, effectively, from the point of view of those outer electrons, those the inner electrons, the electrons in the 1s orbital, are canceling out some of the nuclear charge. The outer electrons are attracted by the nucleus, but they're repelled by those inner electrons. And so the net attractive force on those outer electrons is much less. We say that the effective nuclear charge experienced by that outer electron is only 1+. And so the 2s orbital is pulled in, but it's not pulled in very much. And so this is the how the energy levels look in the lithium atom. And so you can see that the 1s electrons are pulled in very tightly around the nucleus. And those electrons are referred to as core electrons. They're pulled in very tightly. And then the electrons in the outer energy level are called valence electrons. And in this context, valence comes from a root word meaning activity. And the valence electrons are the electrons that actually get involved with things like chemical reactions. When an atom interacts with the world, it's those valence electrons that do things like forming chemical bonds or being transferred to make ions. Those valence electrons are the ones that do all the interesting stuff. And so in the case of a lithium atom, the core electrons have the same configuration as the helium atom. The core electrons are 1s2. And then the second energy level is sometimes referred to as the valence shell. And you can sort of see why the word shell is used, because it is a little bit like an eggshell around the atom. And so we can represent this in the electron configuration by replacing 1s2 with the helium core. And so we can write the configuration of lithium as being a helium core plus a 2s1 electron in the valence shell. And similarly, since it is just the valence electron or electrons that we really care about, when one draws an orbital diagram for an atom like this, it's very common to leave out the core electrons and just to emphasize the valence electrons in the atom. And so typically, if you wanted to represent the electron configuration for lithium, you can write it as the helium core plus 2s1, and then its orbital diagram. Really, the orbital that we care about is the orbital in the valence shell, and in this case, that's the 2s. So, moving further, beryllium is going to be relatively easy. The next electron is just going to go into the 2s orbital, and so its configuration is going to be helium core and then 2s2. And its orbital diagram, if we just want to show the valence shell, is just the 2s orbital with 2 electrons in it. And we'll continue looking at electron configurations in the next video, but for now, this is where we're going to stop.